Hi, my name is Vyacheslav. I want to talk about how we designed a backend for a game called HAWKED. Maybe someone of you heard about it. So, uh, I am who I am. I'm Vyacheslav. I'm lead of the HAWKED backend team for now. And for like 10 years, I worked as a server developer for different kind of products, for games, for B2B projects, for B2C projects, like in completely different areas, and like end up in my games and work on projects called HAWKED. What is HAWKED? Uh, as maybe you don't know. Well, basically, HAWKED is a third-person online extraction shooter, but it's not that important for our talk. The most important part for our talk is that it is a multiplayer game. It has an online part in it, and it's also a live service game. So it contains a lot of meta progression stuff, like you need to store some battle passes, quests, and all kind of stuff that you need persistently store for every player who ever played your game. And let's start from talk how we started this. At some point, we started to design our backend in like knowing that we need to make a backend for a game. We already know what we want to make a session-based game, shooter game, but we haven't known at that point what exactly we will have inside. So we don't know what kind of quest we will have, what kind of meta progression we will have inside, nothing of it. So we need to keep it in mind. And that's the first challenge for us, game design. Game design is hard. It's like not the solution that not the problem where you just have an exact solution and that's all. You always want to iterate to see how things go in, to see what interesting now for players in our field, or what will be interesting in like a couple of years, because the games doesn't make in days, they take years. And that's why our backend should be able to help designers to check their ideas, to see does it work how they intended, does it interesting to use this, all this kind of stuff. And to help this, backend as a part of the whole system need to support this. The second one for game design is the complexity. Sometimes design is simple, just pick some item, store in database, you're great. Read it from database, return to the client, like completely done. But sometimes it's much harder. For example, matchmaking. Matchmaking is like completely different stuff. You can have like 1,000 rules, 1,000 ways to solve this problem, and it's not that easy. And sometimes complexity can be not in like algorithmic stuff, but in connectivity between features. For example, you have a tutorial in our game. You have a tutorial. When you complete it, you need to mark a player completed tutorial. So you have unlocked different kind of features. And when you unlock this kind of feature, some different features will be affected by that. And all this connectivity between features, you need to support it, because you cannot make things isolated from each other. But not only game design is important when you develop a game. Second thing is development itself, because when you make a game, you made like a bunch of features connected together, but except this feature, you should have something else. For example, you want to allow, for example, game designers to run your backend locally to see how their changes in balance or in movement or something will affect them. So you want to help them run everything locally. And second problem with the development is you want to separate the client and backend development. It's really important because the feature, as I mentioned, can be really complex on the backend side and really complex on the client side. And if you don't have a clear boundary between them, so now you need a person who can write both sides simultaneously. But if you have a boundary, you can define this boundary, make it simple, clear, and split it between two teams, and it's great. Also, there is a lot of platforms. You all know about PlayStation, Xbox, Steam, Epic Game Store, Nintendo Switch. There is a lot of platforms, and they all different. Every platform is different from each other, and you need to support all of them. And to help in development, you want to make it simple, like make something common for all of them, make it available for a client, and hide everything else on the backend side. So no one else know about this. It's hidden. And last one is internal services. If you make a live service game, you obviously want to know what happens in your game. Well, I think it's not only about live service game. You always want to know what happens in your game. So you want to support some telemetry data, maybe how your game alive, or like maybe some problems happens and you just don't know it yet because it's like affect 1% of players and they don't like to complain about it. And also the on online players or online games in live service game, you want to have a big system for support players if something goes wrong. Maybe some quest got stuck, maybe some reward haven't been received because our dedicated server crashed or something like that. And we want to be able to handle this easily from the operation side. Okay, we developed our server, but there is an even third part of it. When you develop the server, you want to operate it. So it's like run smoothly, handle thousands, 100,000 of people. How you support it? You also need to additional support for that. You need to support for orchestration tools like Kubernetes or HashiCorp Node or something like that. Because if you don't support this, how you scale, you need some solution for scaling. Also, there is a small remark about the infrastructure. Not all servers hardware equal. Sometimes you have really weak server because like your cloud provider doesn't have anything else at the moment. And you need to keep this in mind. So you need to keep in mind that sometimes you won't get what you want from server hardware. You need to support even this. The second problem with operation is that backend is hidden. You don't see how backend goes. You just run some black box, it works, and unless something terribly goes wrong, you don't even know what happens inside. So to see this, you need some kind of observability around this. And basically, like most common way to handle this is collect some telemetry, in-game telemetry data from inside of the game, collect some metrics, collect some logs with the proper tools to analyze it, or like traces if you can make it work in your case. That's a really nice thing to have. And last one, in operation, as I mentioned before, you need some kind of tools to manage your server. For example, to watch for a health status of your server. Maybe some components going down and you need to know it. Or maybe you already know that your server is in trouble, but you need to like get some data out from inside of this server to test it, to check it on the developer side, because developers don't have access to production and shouldn't have access to production ever. So you should have tools that you can like give to operation team, and they give you some data from that. This was three major pillars for us to keep in mind when we started to design our server. But first of all, why to design something new if there is something else? Maybe someone already solved your problem. Unfortunately, we haven't found any good enough solution for us. There is a lot of companies who already made something similar to that. Like Google, Amazon, and Microsoft all made the product for game management, for games. They call it something like that. But all of them is really limited in what they provide. For example, Agnes is only provide the hosting capabilities, like they solve infrastructure for you, but not anything else. Or Amazon, they also solve the infrastructure problem. So basically, all of them solve infrastructure problem for you. But Amazon also have some additional features. For example, they have a matchmaking tool that helps you with matchmaking in game. On Microsoft side, they also has a feature for authorization. You can handle authorization on different platforms through the platform. But the problem with Amazon, Google, and Microsoft is that they have only cloud solution. You cannot host it on your own hardware. You should use their cloud. And even worse, that they require you to use their cloud even for your tools. So if you write a server, you need to write it for their cloud. That's kind of sad. The last one is a Photon Engine. They have similar solution what we wanted. They have a lot of different stuff inside. It's a really cool product, but they came with a different idea. They solve exactly one problem for you. So we make a simple game, a simple game server. So if you need a simple game server, that's our solution. If you want something else, unfortunately, you need to like do a lot of different stuff. And the second problem with them, and it's only on big scale, is noticeable. They host only on Windows servers. Everyone who knows about Windows servers price can like understand this. Okay, so what we designed, how we were doing this. First of all, we thought about like base ground. What we have as a restriction for us in our product to handle, what we don't want or don't need to change. For example, operation system. Like as I mentioned before, if we want to like big scale, we want the servers only on Linux. It's a cheaper and it's a most common solution for clouds. Like no reason to change anything here. But development is all based on Windows because all consoles is Windows based for development tools. I mean, they require you to have a Windows to like use their SDK, use their tools, and so on. And also, a lot of really nice tools to use is also Windows based. So basically, if you want to develop a game, you use Windows. Except macOS and iOS because they require macOS as a support. So if we made a game for these platforms, we also need to support this. Language, we chose C#, mostly because we have an experienced team in C#. Like we had previous projects made on C# as a server solutions. We had a lot of people who work with C# in desktop tools, like helper tools for the designers, developers, and so on. So we have a lot of expertise in C#, so that was pretty good solution for us. Alternative for that, it was Java and Kotlin, but basically it was pretty similar. And C# was chosen because we make a bet on the other solution that we chose. I will speak about like a bit later, called Microsoft Alliance. Well, and so also C# is one of the best solutions for a server-side development. Like, not much options you have. And third one, it's a hardware. As I mentioned before, we don't have like luxury to have like 512 gigabyte servers for one product because it's quite expensive. You need to keep this in mind. You want to be able to scale your product as much as you can horizontally. You don't want to be like a single server that eats all your money. And first, we will talk about like this middle part of our product. Middle part, we called it core part of our backend. Basically, it contains from two big problems we need to solve. First one, it's a client-backend communication, how we will make our Unreal Engine client to work with our C# backend in such a way so it can be controllable. And second one, how we make a scalable in-game logic. Scalable in-game logic, I mean that there is like thousands of players simultaneously. Everyone do something like take an item, starting a matchmaking, go into the session or something. They all doing something. And you need some way to scale this. So the more player you have, it's more easy to like, it's not harder than small amount of people to handle. And the base idea for second problem, we chose Microsoft Alliance. Well, basically from their words, and basically it's what it is. It's a framework for building distributed application. So they promise you to solve your scaling problem by using it. It's based on actor model. I will talk about actors a bit later because it's a really cool concept, and it's the reason why Alliance is really distributed system. And they promise that they will help you to write simple code without any additional knowledge about how to write a distributed program, and it just works. And surprisingly, it works. Let's dig deeper about Alliance and why it's important. First of all, as I mentioned, actor model. Actors, it's a lightweight objects with some state and some behavior, like pretty simple logic. But both of these parts is managed by Alliance. So they basically say you define an interface with an actor, define an implementation of this actor, and the Alliance will handle everything else about creating this object, calling this object, returning the results or exceptions or anything else. How it helps with the development. First of all, Alliance promised you that every actor is single-threaded effectively. So if you call an actor, like method on an actor, and you call it like 10 times in a row, or not in a row, like simultaneously, all 10 calls will be executed sequentially. In some sequence, it's not defined because they came like at the same time, but they will not interleave. And that's mean that you can use in actor like basic dictionary and never encounter concurrent modification exception. That's most common thing if you work with concurrent development. You have seen this exception a lot. The second thing that Alliance is solved in development process, if you use the mechanic that Alliance is provided for calling actors and calling methods on actors, the Alliance will handle everything about creating and calling this. So the Alliance consists from two parts. It's Alliance client and Alliance node. Alliance client, it's basically you can call actors, but you can host actors on this side. On like node, you can host the actors and call actors. It's not like it solves everything. And how it happens, you just call an actor on one of the nodes from the different node or from client, and Alliance know where in cluster on which exact node this actor is located, or if nowhere, it will create one, load state from the database, initialize it, and then run a method on it. And you don't say anything else from this. You just call an async method, do something. It just works. And as I mentioned, it calls database by itself. It has a simple support for persistent, but because the main idea of actors is that they have small state, you just have a lot of actors, but each individual state is small. You can like basically store this state in database like as one piece and read this state from database as one piece. And Lens allows you to just write some code that this object is a state. It should be stored in database. And you just call like write state async to save it to database. And if you don't call anything, you just work it in memory. It doesn't require you to call anything from database itself. So you basically use it from C# code like explicitly. And one of the benefits of it, Arlayans provide from the box in-memory solution. So you can start your server with in-memory storage, and it will work absolutely the same as with the database. But the only difference that this state would be stored in memory itself and not in database. But all mechanics, all logic you write with the state is working as if it was in database. It really helps with starting your server locally with minimum time. You don't need to start a database. For example, MongoDB for us, you don't need to do this. You just start a server with the memory database and you work with it. There is some cases where you want to like store data to, for example, load it in the next iteration like that. You still need a database, but well, it's more complex cases. And last one is scaling. Scaling that Microsoft Alliance provides you is basically if you follow all the recommendation about how to write an actors, it will be working from the box. And how it works, Arlayans is handling the node allocation. He tracks what node is up and down. And when you create an actor, you choose one of the node to allocate actor there. So basically, if you need to scale up, you can start up a new node, and Arlayans will see that this node doesn't have any load on it, no actors. And it will move some actors from the previous nodes to the new one. Or if you don't allow move, it will allocate new one there. And the old one will, at some point, will disabled and move to the new one. And by their papers, they promise like millions, 10 millions of factors simultaneously. Unfortunately, 10 millions we haven't checked yet, but we tried, and like it's in our live server was like 1.5 million actors simultaneously on five servers, 5 nodes server. So like, yeah, we haven't seen any degradation about like working with actors. Like the average actor call was around like 20 milliseconds. It's pretty nothing for like this kind of system. That was our solution for a game logic, how to write a game logic inside backend. But what about the client backend communication? Because we need to send data to the client and receive something from the client to answer them. And the problem that we wanted to make this boundary between client and server, and to make it, we decided we need some kind of protocol. And we tried to find something. First of all, we looked at OpenAPI, Swagger, if someone else know this name. It's pretty common API protocol. It's written in JSON and YAML, famous. The biggest downside for OpenAPI, you cannot write its schema in JSON and YAML by hand. Just, you cannot write it. You need to generate it from something else, because like, despite its YAML or JSON, it's still so complex. The alternative for that, it's a protocol buffers. And this was nicest solution we had. It can generate code for C++, for C#. It has an already made generators. It's simple syntax, and it limited syntax. You cannot write something that isn't supported on all the platform you have. The downside of the protocol buffers, after our experience, is that you cannot extend it if you need it. For example, because we use an Unreal has some special types, special things inside, so you can generate special code for that. But to generate special code, you need to mark it in the protocol buffers file to make known for a generator that this is a special case. And sometimes it doesn't work, unfortunately. You can solve it with protocol buffer options, and that's how we solved it for our project, but it's not best solution, to be fair. But despite this fact, protocol buffers is really good solution. And also it's really compact. It's a binary format that saves a lot of traffic between the client and the backend, especially if we collect telemetry that it's just the data, a lot of data that we want to know about, like how, what player do in game. For example, on our test servers, for example, we collect even data about how player move on map. So you know, after the fact, you can see how players moved on map, where they been the most, where they haven't been, or maybe there is some issues with the movement system. That's why we used it. We decided that we want to use a protocol buffer as our protocol. To be fair, this question isn't the direct one. The second question that we need to answer at the same time is how exactly we communicate between client and server. There is an TCP protocol. No, thank you. Everyone who works with the raw TCP channels and try to make it secure don't want to do that. So it's better to try something more high level. And first of all, we thought about HTTP protocol. And to make it short, it's simple. It's simple and you can use it. But it doesn't allow you to stream data if you want to. That's major downside. And also it doesn't support RPC in RPC way. It has a REST, but it's not exact RPC. We can argue about that, but it's quite hard to make it HTTP RPC. Next one, it's an gRPC. gRPC is great solution. It's most common in server-to-server communication. It's a great solution. You can use it almost everywhere on the server side. It has a protocol buffers. It has the RPC description. It has a message description. It supports streaming. It supports security from HTTP2, to be fair. But the problem is HTTP2 and LPN technology. It doesn't compile on some platforms completely. We spent some time trying to make it work, but failed, and decided to try to, instead of trying to make a gRPC work with all of its dependencies, to move step back and think about maybe we can try something else. And there is another technology called WebSocket. And it's simple as HTTP. And it supports streaming. And it even has a support in Unreal Engine. So it's really great. But it doesn't support RPC and messages yet. So we decided to make our own RPC. That's one of our handmade solutions. We basically took a gRPC, made the same way as a gRPC implemented on HTTP2, but implement over WebSocket. And so we can use the gRPC generated code on our server side. So we basically don't do anything for generation for server side. But for client side, we still need some generation. And for client side, we wrote some protobuf generator that works with our protocol. But because there is Unreal and Unreal C++, it's not a C++, standard C++, to be fair. So yeah, you still need some support on the client side. Anyway, we already had it. So yeah, we haven't done much difference. So we solved problem between the client and the client instances on the backend to do some logic. But the problem arises that you don't only need some individual logic on the clients, but sometimes you need services that works like separately from your server. Like on this, it's an authorization, it's matchmaking, it's a queue, it's rating, it's like anything that even not we made. It's some like tool from our other customer maybe, because we use it and we need to interact with it. So we cannot build it into our server. So we need some kind of services. And there is nothing new. We just took a classical ASP.NET Services approach. So all of the services, mostly, classical ASP.NET application using a gRPC to communicate with our server. We generate a client for our server and like instantiate one service at a time. These services, I would split in 3 categories. Why we need to be, why these services need to be separate from your game server. First of all, in the singleton services, the problem with them, they require to be in a single instance to solve the problem, as in matchmaking. You cannot solve a matchmaking in several instances fast enough. You need a single instance to solve a single queue for matches. You can split by queue, you can think about some solutions, but it's much, much harder. It's easier to solve this by one service that exactly dedicated to solve this problem. Same for a rating service. Leaderboards, you need to know all players who participate in some leaderboard to show what place player have in rating and so on. The second one is the shared services. It's the services that you create and want to share with different with other projects because, well, they're useful, but they are not your backend. Their own backend. So you want to make something separate, something independent of your backend. For example, the telemetry is like one of the biggest our example. That's a really complex system to collect a lot of data, to make it able to analyze it, to see graphs and so on. And you want to reuse it on different projects. So we just made a separate service for that. And the second example, it's a community support tools. Well, it's not first game in our company, obviously. So we already have some tools to manage a community. Why these tools shouldn't not be reused on our project? So we need to interact with them, provide some integration point for them to us. So you just write some piece of code that do something for them. So they're happy, we're happy. And last one, it's a heavy load services. It's very awkward thing because sometimes some services can be under heavy load, like authorization. For example, some malicious users decide to DDoS your authorization. And you don't want to affect your game at all. Yes, new people cannot log into your game. That's a problem. But if because the authorization server is under DDoS and it affect your game server, everyone else have a problem. You have an even bigger problem. Or Q is same example. Or sometimes you can have some service that, for example, need to process a lot of data, batch processing, and you want to share it to split it to the different server physically, so it can use as much resources as it wants, and you don't be affected by that ever. Also, I moved this into separate like the services section. there is a lot of things that you need to solve by moving data outside of your game. And there is 3 big categories for that. Resources. Resources is some static data that you need to share between client, dedicated server, and your backend, because obviously we make a same game. So you need to like share some data between them. And you need some way to share this, to make it available for a client, make it available for a backend, make it available for a dedicated server. In our project, we have this data is located inside the game, inside our Unreal Engine project. And when we build this project, we export this data, this shared data, in separate file, and share this with the backend, because like we have most of this data located inside our game. The second problem is caches. Well, all these mechanics I talked about work great, but sometimes there is one piece of data that needs to everyone. Or, for example, you have a person with 200 friends, and this person should know about all his friends at all time, because we want to show this to people so they can interact between each other. It's a social game. And that's why you need some kind of separate external cache to share this data, because we have distributed system. Now, you cannot share cache data on single node. You need to cache it somewhere outside. And like as a simple solution, and we use it as a Redis, like we just have this service moved outside and say that if you want to use cache, go there. And the global state. This one is similar to caches in some way, but it's not only about provide data, it also allows to subscribe to this data. For example, the player presence. Player presence is, do player online, offline? Is he in matchmaking, or maybe in a match, or maybe doing nothing? And we want to share this data as fast as we can to other players, for example, friends, or in squad frames, or we have such a thing as a hideout. It's our Rift Wake. It's a place where all players located between matches, and you can see what players do on this in this place, even if they are not on your friend list or somewhere else. So yeah, the global state is different because it's a more complex system that allows you to subscribe to data. We basically solve this by Orleans means. We created a special actor that solved this problem for us, that allocates for each player online. And if player isn't online, so it's offline, it's good. So there is no actor now. And if it's online, you can ask it to subscribe for data that solves. And it works surprisingly well for like even our synthetic tests for 1,000 people interact with each other like in all-to-all manner. It surprisingly worked well. It's about development. So we decided that we want to use Orleans as our core part. We made all these kind of services around us. So we need to deploy this somewhere. And somewhere is our servers, because we use self-hosted solution with our service. So we deploy it to our servers using HashiCorp Nomad. Not the Kubernetes, unfortunately, because we haven't had enough experience with it. As I talked about observability, there is an observability tools we used to do like all the things I was talked about. And we use a Grafana stack, like Grafana for dashboards, Grafana Loki for a logs collection, Prometheus for a metrics collection, and Grafana Tempo for a trace collection. And all of this is concentrated in Grafana UI, and we can basically observe every data that we have. And the last one thing I want to mention here is the configuration management. You always want to have an ability to change configuration on the fly in your server, because something will go wrong on your live server, and you want to have some ability to change it. For example, we use HashiCorp console as a key value storage, and we just made a feature in our server that subscribes to this key value storage. And if you want to change something and it's available for subscription and it's available for changes, you can just go to console, add some key and some value. You need to be very careful to not break your server, but it's a last resort if something goes wrong, and you can fix it. Basically, at some degrees, you can fix it. For example, we changed the timeout for our external Steam profiles because for some reason Steam started to respond in 10 seconds at some point, and we need to fix it fast. So we just raised our timeout and started to investigate what exactly went wrong. Well, and that's basically all about like designing a backend. Obviously, it was only like main part. There is a lot of details inside. And what we want to do next. From the HAWKED project, we've seen that this works really well for our project. And we want to share this to other projects that we have in company to reduce basically the time you spend to build a backend for a game. Because our backend is nothing special for exactly HAWKED. It like a lot of stuff there is to any backend you have like in any game, if you even need a backend. Maybe not only MMOs. That's only thing I can think about that doesn't fit into our approach mostly. But even then, you can think about something. And second one, we want to share knowledge about why you need to think about backend, why you need to think about all this stuff that I was talking about. Because you build a project every time from scratch, and okay, you can switch from Unreal 4 to Unreal 5, and that's a big leap, and you change a lot of stuff. But on the backend, mostly you use the same stuff. You don't change much on the backend. You just need to use it. And sometimes someone takes this too much and they stuck with technology 10 years ago, and they need to use their new knowledge also. That's all. Thank you.